In the previous lecture, we explored how a wind turbine interacts with the airflow around its rotor. In this session, we will take a broader view, examine how wind turbines interact with each other within a wind farm setting. By the end of this lecture, you should be able to explain the importance of wake effect on wind farm performance, understand how wind turbines interact and why this affects wind farm efficiency, identify both high and low fidelity modeling approaches for wind farm aerodynamics, describe some strategies to mitigate wake effects. Wind turbines are often clustered together in what we call wind farms, mainly due to economic considerations and the limitations in land or sea space. However, as shown in this famous photo of an offshore wind farm, the presence of one wind turbine affects the inflow conditions of the downstream rotors. The region behind a wind turbine rotor is called the wake region. As we learned in the rotor aerodynamics session, a wind turbine rotor extracts energy from the wind by exerting a force on the incoming flow. This causes the wind speed to decrease as it passes through the rotor plane. Additionally, as the blades rotate, they disturb the surrounding air and introduce turbulence into the wake flow. As a result, the wake regions experience lower mean wind speed and higher turbulence intensity. This directly leads to decreased power output and increased fatigue loads on downstream turbines operating in the wake of others. This loss in efficiency caused by the wake is known as wake effect. Now let's take a closer look at what happens to the airflow after it passes through the rotor. As you can see, in the wake region, the wind speed is significantly reduced. Over distance, this slower flow gradually recovers toward the free stream velocity, a process known as wake recovery. This recovery is primarily driven by turbulent mixing between the wake and the surrounding faster-moving air. However, research has shown that this process is relatively slow. Even 8 rotor diameters downstream, the recovered power is only about 50% of that in undisturbed conditions. Given that turbines in a wind farm are typically spaced 4 to 10 rotor diameters apart, many of them will inevitably operate in the wake of upstream turbines. In fact, studies have shown that the wind farm can suffer up to 40% reduction in aerodynamic performance caused by the wake effect compared to the first-row turbine operating in the undisturbed flow. The extent and the nature of these wake interactions depend on several factors: the spacing between the turbine, the wind directions, the turbine's operational conditions like yaw and pitch, the surrounding atmospheric conditions such as turbulence intensity. To accurately capture the complex interactions between wind turbines and between turbines and the atmospheric boundary layer, we rely on high-fidelity modeling techniques. These slides show an example of CFD modeling for a 20 by 9 wind farm layout. The video on the right illustrates how the wake from a single rotor interacts with the neighboring turbines and the surrounding atmospheric flow. These models are essential for understanding detailed wake behavior and for predicting wind farm performance under realistic atmospheric conditions. While high-fidelity models like CFD are great for detailed analysis, they are too computationally intensive for real-time control of all large-scale wind farm optimization. That's where efficient models like analytical or empirical engineering wake models come in. These models are fast and sufficient for layout and control design. This slide compares velocity deficit predictions from several analytical wake models with LiDAR measurements. As you can see, there are differences in accuracy, and selecting or improving these models for various configurations is an active area of research. Due to the significant and often unavoidable wake effects in wind farms, considerable attention has been given to developing strategies that can accelerate wake recovery, aiming to reduce wake losses and improve the overall efficiency of wind farms. These strategies can generally be categorized into passive and active approaches. Among the passive approaches, two main types stand out: rotor level design modifications and the wind farm layout optimizations. The animation on the left illustrates several rotor modification concepts that introduce rotor asymmetries, such as windlets, fins, blade extension, deflection, and azimuthal offset. These changes aim to modify the wake structure and promote faster wake recovery. On the right, you can see an example of layout design using tilt rotors within a wind farm. This helps reduce wake overlap and improve inflow conditions for downstream turbines. Alongside passive strategies, several active wind farm control methods have been proposed to mitigate wake effects. Some of the key active strategies include dynamic induction control, helix control, wake redirection, and wake repositioning, etc. In the animation on the left, we can see examples of dynamic induction control and helix control, which use collective and individual cyclic pitch control respectively to modulate the loading on the rotor and influence the wake dynamics. The animation on the top right shows yaw-based wake steering control, where the upstream turbine is intentionally misaligned with the incoming wind using a yaw offset. This deflects the wake away from the downstream turbine, reducing the wake overlap. The animation on the bottom right illustrates the rotor repositioning, where the rotor is physically shifted laterally by utilizing the additional degrees of freedom available in floating wind turbines to reduce the wake interference. As a result, the downstream turbines is exposed to higher wind speed and experience less wake-induced energy loss in both cases. However, the success of these strategies depends on careful design. For example, the yaw offset must be chosen to ensure that the power gain of the downstream turbine outweighs the power loss from the misaligned upstream turbine. Similarly, the effectiveness of wake repositioning depends on flow conditions, site constraints, and the turbine flexibility, etc. Overall, the success of active strategies must be validated across a wide range of operating conditions and with careful considerations of their economic feasibility. In this lecture, we have learned why wake effects from a single turbine are critical to wind farm performance, how turbine-turbine interactions reduce efficiency and increase loading within a wind farm, the role of both low and high fidelity aerodynamic modeling in understanding wind farm aerodynamics, various passive and active strategies for mitigating wake effects and improving wind farm efficiency,